This is lesson 11.1 extension 1, and this video is a continuation of lesson 11.1 about hydrogeology related with contour lines and groundwater flow directions lines. I highly recommend to see the previous video in order to have a better understanding of this second video related with hydrogeology. In this video, the main topic is going to be again contour lines and groundwater flow direction lines, but we are going to see what it represents the groundwater elevation when we have one well, when we have two wells, 3 and 4 wells, and we are going to see how 3 wells it's not enough to define the groundwater flow direction. Also, we are going to be working with triangular interpolation with 3 and 4 points, and we are going to see different kind of interpolation methods and how the final decision depends on the professional, not on the software interpretation. Okay, let's go to do it. In this exercise, we are going to see what groundwater elevation represents at the space. Let's go to imagine that we have one well and we have the water table right there, and that one is the surface. Then we can say that in this point right there we have 3 coordinates. That one is x, y and z. And then as we have 3 coordinates, this point can be represented at the space. Okay, the coordinates x and y, they are provided by for example, for the UTM coordinates or geographic coordinates with latitude and longitude, something like that. And for the z, that is what is the depth of the water table with respect to an absolute vertical datum or with respect to a virtual plane. Okay, as we saw at the other video. Then we are going to represent this point at the space, and that's the goal of this draw here. Okay, we have one point with 3 coordinates, x, y and z. The x is the number 2, the y is the number 4, and the z is number 3, and it represents the groundwater elevation. Okay, that's negative numbers. Okay, and when we have one point at the space, what kind of information we have? Let's go to see that one in a draw. When we have just one well, we cannot say anything about the groundwater flow direction. It's not enough. We can say we have groundwater, but we cannot say anything more. Even we don't know if that one is a paired water table or the water table is quite continual under the ground. And also for the direction could be any direction for the groundwater, right? Groundwater can move in any direction. We have just one point at the space, and that one cannot provide us any information. Then one well at the space just define one point at the space and cannot provide too much information. Now let's go to see what happened with 2 points. With 2 points at the space, we can define a line. From here to here we have a line. Now let's go to see what it represents at the groundwater contour lines and flow direction. When we have 2 points at the space, we can define a line. Okay, like this one, we have 2 wells, and both of them are penetrated the aquifer. Let's see what kind of information we can get with 2 points. We can define a line like this one, okay, and this one it's a line at the space. However, even if we can see this value is higher than this one, that it's not too much information, because the contour lines could be, for example, something like that. And groundwater is moving like this, but also could be something like that. And groundwater is moving like this, changing the direction. Before it was like this, now it's like this, and also could be something like this. Let me think, just to force a little bit. And now the direction of the flux is like that. Could be also something like this. And now the direction is something like that. As you can see, there are a lot of different options. Then if we have, that line is quite horrible. Then if we have 2 points, we cannot say too much about what is the direction of the groundwater. It's not enough to decide what is the direction of the groundwater. Now let's go to see what happened when we have 3 points. When we have 3 points, I show you in this draw, we can define a plane at the space. Something like that. And that one is going to be a specific direction. And now let's go to see what happened when we have 3 wells and what kind of information we can get. When we have 3 points at the space, you know, and all these 3 points are wells that are penetrated the aquifer, we can define the plane of the groundwater table. Okay, that plane is going to be defined for this triangle. Let me change the color. And now with this information, we can make a triangle interpolation to see what is the flux direction. Okay, but I can anticipate that could be something like that. Okay, and the flux direction is going to be something like that. Right? But the point here is it is enough, 3 points, to define the groundwater flow direction. The answer is not. It's not enough. You need more points at the space to define a proper plane. Okay, now I'm going to show you an example. In this example, I'm going to show you 3 different scenarios that can happen when you have just 3 wells and you are trying to define the groundwater flow direction at the space, right? Here we have 3 wells. As you can see here, they define this plane here, and with this plane we can make a triangle interpolation and get what is the contour lines. Okay. And one possible scenario could be something like this one. You can see what is the value here for the every contour line, and here is the value for the groundwater elevation. As you can see, this scenario could be total possible, right? We have a value here that is 98.145, and that one is very close to the contour line of 98. We have 97.245, that it's very close to this line, and also 96.325, that's very close to this line. Okay, that it's a possible scenario. However, this one could be also a potential X scenario, and that one, it's also a good interpretation, right? Because we have here the 96, and here we have 96.325, and this well is located here. For the 97.245, we have here this line. It represents the contour line of 97, and for 98, we have this line, right? That it's a quite forced scenario, right? Because the contour lines are not equidistant, and it makes a different geological interpretation, right? It means that here we change from one kind of sediments to a different kind of sediments, and that one justify why the groundwater table could make something like this. Because here, if we make a section, for example, let's go to suppose that one is the surface of this terrain, and the interpretation of these contour lines is going to be something like that we have quite flat groundwater, but suddenly the water goes like this, right? We can justify that one, for example, if we have a lateral change of geology, right? Maybe we will have here something like this one, and in this area we have sand. That's a cross section, okay? And in this area we have a clay, for example. And then the behavior of the water table, when the water passes from one medium to a different medium, the behavior is different, okay? Even that scenario could be possible. Another potential scenario could be this one, okay? As you can see, the X scenarios, that is a quite extreme example, but just to let you know that 3 points, it's not enough to define what is the groundwater flow direction, and a lot of things can change. And if you don't know what is the groundwater flow direction, you can make a lot of mistakes when you are trying to explain what is the movement of the contaminant. In this case, for example, if we have a contamination here because there is a spill of, I don't know, gasoline, for example, in this area, and we are thinking the groundwater is moving in this direction, maybe we are going to start to install some wells, for example, over here, and over here, right, to avoid the contamination spread. But if we miss that the real groundwater flow direction is this one, we are going to install these wells here, okay, because we are thinking that the groundwater direction is this direction. However, the contaminant is moving in this direction. And with these wells, we are going to allow to move the contaminant in this direction. Okay? Then to know what is happens also here, if we install the wells here, and the contaminant is moving in that direction. Okay? That is very important to know what is the groundwater flow direction. And 3 points, it's not enough. Now let's go to see how we can make a triangle interpolation with 3 and 4 wells. Okay, let's go to do it. We are still working with this plane. Okay, here is the plane defined at the space, and now we are going to be working with 2 dimensions. Okay, but also we have the z coordinate because of the elevation. Okay. We have the x coordinates for this point here, and the y coordinate for this point here, and also we have the z coordinate because of the elevation of the groundwater. Okay, as it represented here, 2, 4, 3, 2, 4, 3. Okay, now let's go to do the triangle interpolation for this scenario. In order to do the triangle interpolation, we have to measure the distance from here to here and divided this segment between the difference between 12 and 3. In this case, we have to divide this segment in 9 pieces. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces. Okay, that is a piece from here to here. That is another piece from here to here, and these pieces has to be totally equidistant. Okay, then we take the measure from here to here is this measure, then we have to divide it between the difference between this point and this point. Okay, that's 12 minus 3, that's 9, and we divide this segment between 9, and this is the result, and this is the distance for every piece of these ones. Okay, and we have to do the same for this segment and the same for this segment. Okay, then we have to assume that this point here, let me take this one out, this point here at the center, the elevation is 3. Here at the center, the elevation is 6, and the same here at the center, the elevation is 12. Then this number is increasing from here to there in that direction. Then that one is going to be number 4, number 5, number 6, and etc. The same here, this number is increasing from here to here. Then that one is going to be number 4, number 5, number 6. Okay, the same here, number 7, number 8, number 9, 10, 11, and 12. Then we have to join the points with the same groundwater elevation. Okay, in this case, this is number 4. Number 4 is going to be something like that. Number 5, number 6, number 7, number 8, 9, 10, 11, and 12. Okay, and in this case the groundwater is moving in this direction. That's the triangle interpolation for 3 points. As you can see here, that's the result. Okay, that's the final result when we have 3 points for the triangle interpolation. Now let's go to see what happened when we add one more point to this X scenario. Now we have a plane defined by 4 points. 1, 2, 3, and 4. Okay, and now let's go to do the triangle interpolation for this case. What happened in this case that we have different kind of interpretations, because we have this triangle here and this triangle here, and we have to do the triangle interpolation for every triangle. Okay, but also there is a different way to do that one, because we can do something like this also. This triangle here, and this triangle here. Okay. Then for the first interpretation with these triangles, the result is this one. Okay. This is the points we have before, and this one is the new point. Okay. Then I did the triangle interpolation for this one and for the other triangle, and I get 3 different points. Okay. And then what I did is join the lines. As you can see here, for the triangle interpolation, we have something like this, where the groundwater flow direction is moving like this. For the other triangle interpolation, that is this one, we have something like this. Here is moving like this, and then here for the other triangle forced to do something like that. As both interpretations are a little bit different, as you can see here and here, I decided to pick up something at the middle between these two interpretations and created my own interpretation. That's my own interpretation, okay? At this point, I want to say something really important. When we are doing interpretation, and when we are using a software to modulate the contour lines, that is just a tool that is going to help us, okay? When we are doing an interpolation with a software, you have to be aware that the software is not a hydrogeologist, it's not a geologist. The final solution is the solution that the professional is going to provide. It's not the software, it's not about the software, it's about the professional, right? For example, in this case, as you can see, the contour lines are doing something really weird, you know, this curve here. If we make a section from here to here, and we see this point here is low, is smaller than this one. That one is going to be 7.65, something like that. If we make a section, we are going to have here groundwater doing something like this. Okay, and that one is going to be the surface. Okay, and that's the interpretation for this one. As I think that kind of thing is not going to happen, I have to do my own interpretation as a professional, right? Because the software is not going to provide me that interpretation. You have to do that one. You have to use your knowledge and your education to try to understand what is the solution that it's more close to the real scenario. And the software just is going to help you, okay? Now I'm going to show you different kind of interpolations that we can do with 4 points, and you are going to see that every interpolation is going to provide you a different result, okay? Then you have to decide how you want to use that information. But let me tell you that I saw a lot of groundwater flow maps where there is no interpretation. It's just the results. They put the numbers on the software and they do the interpolation, and they took that interpolation and they use that one to make the groundwater flow direction. And that one is totally wrong, because you need to do a hydrogeological interpretation, okay? Even I did these 2 interpretations by hand. That is a triangle interpolation. I didn't use any software because it was just 4 points and it's quite easy. When you have a lot of wells, for example 15, 16 wells, right, it's more easy if you are using a software to interpolate the information, interpolate and also extrapolate, okay? You don't have to keep just inside this triangle because you don't have information outside of the triangle. That's also a very important point. If you have these 4 points, okay, you don't have to limitate it just for the information you have inside this area. That is going to be interpolation, you can also use the information outside here, right? You can use also this information, because to be honest, you only have information here, 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 and here. The rest of information you are providing, that's interpolation or extrapolation, right? Then as a professional, you have to decide what information you are going to use. This result is not based in any kind of interpolation. That's my decision. I decided to do something like that because I thought this solution is not good, and this solution also is not good. And I decided to try to create something at the middle, and my best solution, it was this one. But any software is going to provide you this solution, because that it's my solution. I decided to do this groundwater flow map like this. Now let's go to see what is the interpolation results for different methods. This is a software interpolation, extrapolation based in different methods for 3 points. Okay, that was our 3 points. 1, 2, and 3. Okay, the first method, it's the triangulation with linear interpolation, and that's the method we use for the example 3 points. Is the same result. Here we have the groundwater flow direction. Is this direction. The next one, it's a very popular one, Kriging. It doesn't make any sense to use Kriging for 3 points, but it's just an example, right? Another kind of interpolation. And in this case, you can see there are some contour lines that made some curves. Okay, and here we have not just interpolation, we have also extrapolation outside of the triangle. Okay, as you can see here also for this example, looks like there is an area of recharge here, and a kind of cone of depression here, that it doesn't make any sense, right? Remember that in this kind of contour lines, that it's the depth of the groundwater. Okay, that's the deepest point. Okay, well, it was that one, that it was 12. For the last one, it's also pretty interesting. That's a minimum curvature, and also there is extrapolation. Okay, because we are outside of the triangle where we are going to do the interpolation, and we have some results outside of the triangle, and that's extrapolation. Okay, this is the. There are more methods, but I took that one just as example. Okay. Now let's go to see what happened with the 4 points. For the 4 points interpolation, we have an interesting results. For example, for the first one, for a triangulation with linear interpolation, we have the information inside the triangles. Right. As I said before, there are a couple of triangles. In this case, the software used these 2 triangles instead to use these triangles here. Okay, instead to use this one and this one, the software used the blue ones. Okay, and it's interesting how the software make the interpretation, because as you can see here, these lines, this line here also, we know the groundwater table never is going to do something like that, right? Also for the Kriging, well, as you can see here, the 4 points in this case is this one, this one, this one, and this one. Okay. For the 3 points, it was this one, and this one. And for 4 points, we add this point here. For Kriging, again, it doesn't make any sense to do the Kriging with 4 points, but just as example, okay? We have the same scenario as 3 points, like there is a area of recharge here and area of extraction here. Because of the contour lines, they are doing something like this, right? From here is something like this. That also doesn't make any sense. And for the last one, that is a very interesting case where we are doing the interpolation with polynomial regression, and that's very interesting because the result is the same result as I did, but I didn't use any software. I did the extrapolation and interpolation later, and it is the same result. Let me show you. This is the result I decided, and it was a mix between this one and this one, and it's like the polynomial regression. As you can see, it's more or less the same. And now, to finalize this exercise, I am going to show you the 3D model for every X scenario. First, let's go to start with the 3 points. This is the first case for 3 points. 1, 2, 3, and this case is the triangulation with linear interpolation. Okay. As you can see, the interpretation, it's a flat plane. Okay, pretty standard. Let's go to see now the Kriging. That's the 3D model for the Kriging with 3 points. As you can see, the points are there, 1, 2 here, and 3 over there. 3 over there in that corner. And as I said before, I don't like too much this model because it made some contour lines with curves, as you can see here, this kind of shape that we was talking before, that looks like a cone of depression there, and also an area of injection over here. However, Kriging is the most popular to interpolate contour lines, but you need to know how to use it, and it's not easy to use Kriging to do interpolation. It's a very complex method, but the goal of this video is not to explain how to use Kriging. Okay, now let's go to see the last example, the minimum curvature. The minimum curvature in this case, for me, it's my favorite. Okay, the plane it's very flat and make contour lines straight ahead. That it makes sense to me, and it's really good. But as I said before, 3 points it's not enough to define the groundwater flow direction. Now let's go to see the 3D model for the 4 points interpolation. In this case, the first example, it's for triangular with linear interpolation. As you can see, we have the 4 points, 1, 2, 3, and 4. And there is a weird shape here, as you can see, because of the triangles interpolation, right? That it's quite unnatural. You see there, because of the triangle interpolation. Now let's go to see the next one. This is the Kriging interpolation for 4 points. 1, 2, 3, and 4 there. Okay, as I said before, I don't like too much because of this kind of shape here at the water table. That doesn't make any sense also. And also here, like there is a recharge area there. Then I'm not going to use Kriging in this case if I'm going to interpolate, because the plane at the space for the water table doesn't make any sense. Okay, let's go to see the last one. This is the Polynomial Regression, and for me it's the best one, and it's the model who has the best kind of plane at the space. For me it's the one who is represented better the reality. Okay, it's just one plane, pretty flat, nothing weird. That for me is the best. Okay, then as a conclusion, we can say that if we have 3 points here, 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 and we have a groundwater direction, that direction can change when we have 4 points. Okay, and then 3 points is not enough to define what is the groundwater flow direction. We need 4 or even more, 5 points. And also, it is very important where these points are. Let's go to see a few examples about the location of the wells. Let's go to imagine that we want to make a hydrogeological characterization of this site. Okay, for example, this site could be 120 by 160 meters. It's not a really big site, but it's big enough. Then let's go to think where is the best way to set up the groundwater wells. Okay, for example, if the contamination, there was an spill here, for example, I'm going to recommend to install around 6 wells. One here, one here, one here, one here. There is 4 wells already. One here, 5, and something like here, 6. Okay, to make sure we can cover all the area and we can cover all the flux directions. Okay, these locations for the wells are very strong, and it's really good for the interpolation and extrapolation. As you can see, the wells are installed at the corners of the site. Also, we have one well at the source of contamination, and it's a pretty good location for the wells. Okay, and now let's go to see what is not good. For example, if we know that is the source of contamination, as we said before, more or less, what is not good is to install all the wells very close to each other at the source of contamination. Even if we install 5 wells or all these wells, they are very close to each other, and it's just representing around 15% of all the site. Okay, that is not a good location for the wells if we want to make a hydrogeological characterization of all this area. Okay, then put all the wells together is not good. This is going to create a really model for the groundwater flow direction. Other thing that I saw, and it's pretty common, is to put the wells in a line. Something like this it's no good. Okay, because in this case you can imagine, for example, if all these points has the same groundwater elevation and the contour line is something like this. Let's go to change the color. We are missing a lot of information because this represents a line, and we have one line and one point to do the groundwater flow direction. And our groundwater flow direction is going to depend on just one point. That is going to be this one, right? Because all these ones are at the same contour line, for example. And if something wrong with this one, all our groundwater flow direction is going to depend on this point. Then to put our walls in a line, it's no good. Even could be a worst scenario if we have to install 5 walls and all these 5 walls are at the same line. Then we cannot do anything with this one because these points just are representing a line. There, let me change the color. They are not representing a plane, they are representing just a line. Even if we have 5 walls, 1, 2, 3, 4, 5, 6 walls, we cannot do anything because this is not a plane, this is a line at the space. Even if we have to install just 3 walls, and these 3 walls are doing something like that. 1, 2, and the 3 walls are not at the same line, but they are very close to each other. I mean, something like this. Sorry. This one is also very weak way to try to define the groundwater flow direction. If we have money just for 3 walls, it's better to do something like this. The walls very separate with a big distance between them, because this way to define the groundwater flow direction is going to be stronger than the other way. Okay. Also be aware that if, for example, the contamination area is over here and we start to do the boreholes here, for example, we say, okay, we are going to install 2 of them at the source of contamination, then we are going to make a drill here, also here, and also here. Okay, something like that. Be aware that the background concentration for the soils is different at the background concentrations for the groundwater. Okay, these wells, this borehole here could be a background for the soils. Also this one and also this one, because they are out of the area of contamination. Okay, but for the groundwater could be different, right? Because maybe if the groundwater is moving in this direction, that's the contour line, something like that. The groundwater flow direction is, let me put a different color, sorry, and the flux is moving like this. This well is not going to be background for groundwater. The background for groundwater is going to be a well over here. Okay, that's a very important concept. we are thinking we have enough wells to define the background concentrations for the groundwater, and that's not true. That's for the soils, background for the soils, and this one is background for the groundwater. Background for the groundwater has to be up gradient, not down gradient.